In this screencast we will focus upon McCabe-Thiele's graphical method, but before we do that we will talk a bit about separation, XY diagrams, non-ideality and azeotropes, and then finally McCabe-Thiele's graphical method. So why do we study separation? Well, in any kind of production you need separation to, for example, take away impurities in raw materials, take away byproducts in your final product. Perhaps you want to separate unreacted reactants so that you can recycle them into your reactor. There might be contaminants in the exhaust air. There might be contaminants in the water that leave the system, and you might want to separate them, either to recycle the contaminants or to use them for some other purpose. So how do we separate? Well, I suggest here that you spend some minutes by yourself, or preferably discussing this with some fellow students. What separation methods do you know, and what physical chemical properties do these different methods rely on? We, however, will continue and talk about distillation. And distillation is a separation process based on differences in volatility or vapor pressure. A rule of thumb is that if distillation is an option, then choose distillation, because distillation is a very well researched separation method, and there is a lot of knowledge out there of how you can use distillation in different circumstances. Energy is an issue in distillation, and we will come back to that after Christmas when dealing with heat transfer and heat exchangers. We have previously seen how you can create a system curve for constant temperature, but that is not so convenient when dealing with distillation. It's far more convenient to deal with constant pressure. So for example, when you reduce a tasty wine sauce in your kitchen, you don't have constant temperature, you rather have constant air pressure. So how do you get the system curve at constant pressure? Well, you simply repeat the steps that you did for creating a system curve for constant temperature, and then use that data to cut your information in another way, so you get constant pressure instead. So for ideal binary mixtures, we can easily calculate interconnected values of liquid composition, gas composition, temperature, total vapor pressure, etc. And we can draw these as functions of each other in different ways. We can draw, for example, the gas composition as a function of liquid composition for a given total pressure, which is used in the McCabe-Thiele's graphical method. We can draw enthalpy as a function of liquid composition, and so on. So we can get diagrams like this boiling point diagram, but in McCabe-Thiele's graphical method we will use XY diagram, where we have the liquid composition on the x-axis and the gas composition on the y-axis. And this assumes that we have a boiling liquid which is in equilibrium with a condensing gas. We have already mentioned in a previous screencast that you need to use activity coefficients if you have a non-ideal mixture, if you want to calculate this kind of diagram. But why is it that some mixtures are ideal and some mixtures not ideal? Well, in an ideal mixture or a solution, the forces between different kinds of molecules are equally strong. So the forces between molecules of kind A are equally strong as the forces between molecules of kind B, while in a non-ideal mixture the forces are different. So for example, the forces between the B molecules might be much stronger than the forces between the A molecules. This means that for a mixture to be ideal, the molecules must be very similar to each other. If we have positive deviation from ideality, this means that the partial pressure of B will be much higher than ideal at high compositions of A, or low compositions of B, that is. So what will the system curve look like? Well, the system curve will be depressed at high XA, at high molar fractions of A. And it might even go below the diagonal at high molar fractions of A. If it goes below the diagonal, we will have an azeotropic point at the place where the system curve crosses the diagonal. So what is an azeotrope? Well, if we have a boiling liquid that is in equilibrium with a condensing gas, and both phases have the same composition, then the system has an isotropic point. Ideal solutions are never isotropic. If we have positive deviation, we can get a boiling point minima. And here is a question for you to ponder on. What is the boiling point of a liquid with the molar composition 0.2 in the liquid phase? And what is the composition of the gas formed at equilibrium from that boiling liquid? We will, however, continue with solving an example using McCabe-Thiele's graphical method. And the example is taken straight from an exam in 2009, where a benzene-toluene mixture containing 42 mol% benzene is to be separated in multiple steps. In the first step, a distillation column with a reboiler and a partial condenser is to be used to separate the flow into one holding 70 mol% benzene and another holding 10 mol% benzene. Question A. How many physical trays are needed in the column if the feed consists of 75% saturated vapor and 25% saturated liquid? The reflux ratio is 1.5 and the overall tray efficiency 40%. Question B. What is the minimum reflux ratio? Okay, the equations we have are the equations for the upper operating line, where we can use the reflux ratio. We have the Q line, we have the lower operating line. And we identify from the text 42 mol%, that's the composition of the feed. 70 mol%, that's the composition of the distillate, because then benzene is more volatile than toluene. The convention is to write the most volatile component first. 10 mol%, that's the bottom product, and 75% saturated vapor and 25% saturated liquid in the feed means that 75% is already evaporated, which means that to evaporate the last 25%, that takes 25% of the energy compared to the evaporation enthalpy at the boiling point. The reflux ratio is 1.5 and the overall tray efficiency is 0.4. We must note that the distillation column is equipped with a reboiler and a partial condenser, not a total condenser, a partial condenser. And we need to calculate the number of physical trays and the minimum reflux ratio. So to summarize, we have R equals 1.5, XD 0.7, XW 0.1, ZF equals 0.42, Q equals 0.25. We have a reboiler, a partial condenser. We need to calculate the number of physical trays and the minimum reflux ratio. And we actually also will need to calculate the feed location, and we will do that in some detail. The solution strategy for McCabe-Thiele's graphical method is to first draw the diagonal, if that's not already drawn. Then we draw the upper operating line, the Q line, the lower operating line, and then we draw steps, where each triangle we draw represents one equilibrium stage. The upper operating line, we have R equals 1.5 and XD 0.7. So we identify XD equals 0.7 in the diagram. From the equation of the upper operating line, we can figure out that the line must start at the diagonal at XD equals 0.7. And it must cut the y-axis, where XD divided by R plus 1 equals 0.28. That's there. So we draw that line. And we can check this slope by looking at the equation again and see that R divided by R plus 1 is the slope, and that's 0.6. And we can draw a triangle. If we go 2 steps to the right, we go 1.2 steps up, which means that we have a slope of 0.6, so that's okay. Next is the Q line. We identify first ZF for 0.42. We draw that line. And we can identify in the equation for the Q line that this line must cut through the diagonal at ZF equals 0.42. Now we have Q equals 0.25, which means that the slope of the Q line is Q divided by Q minus 1, which equals minus 0.33, and that's a line like that. Time to draw the lower operating line. There we identify that we have xw equals 0.1, and the lower operating line must go through the diagonal at xw equals 0.1. We draw the line through the intersection of the upper operating line and the Q line, like this, and then we're done. And it's time to step. In this course we will begin from the top, so we begin by drawing a line like this, and then we make a vertical line and a horizontal line, and we continue like this. Then the question comes, when do we switch between the upper operating line and the lower operating line? Well, the thing is that we should switch as soon as we have passed the place where the two lines intersect. So we switch now, and this is the optimal feed location on the third triangle, the third equilibrium stage. And then we continue drawing steps like this. What we're doing here is actually solving a mass balance and solving the equilibrium problem. So the line here, the system curve, is the equilibrium between a condensing gas and a boiling liquid, and the line here is the mass balance for the upper part of the distillation column, and the line here is the mass balance for the lower part. So by drawing a line from here to here, we solve a mass balance. Okay, time to think about the reboiler and the condenser. The reboiler is one equilibrium stage, and the partial condenser is also one equilibrium stage. So the top thing here is the partial condenser. And then we can count how many triangles we did. We did 1, 2, 3, 4, 5, 6, 7 almost. Almost 7 equilibrium stages. Feed is on stage, well, it's on equilibrium stage 3, but if we think of what equilibrium stage within the column, we must deduct the partial condenser, so that's on equilibrium stage 2 inside the column approximately. To get more exactly, we take the feed is on stage 2 plus something. Well, how far should we get? Well, we can take this distance here from this line here to this line here. So how far away are we from the place where the two lines intersect, the two operating lines? So small a divided by large A, and then we deduct 1 because we have a partial condenser up there. So that's 1.86. Get. The total number of equilibrium stages, that's 6 something, and we do the same thing here. We take the distance from this line here to that line here, straight above the intersection with the diagonal. Compare that with the distance from this vertical line here to that vertical line there, and we get 6.83. Now, we wanted to calculate how many physical trays are needed inside the column. And since we have 6.83 equilibrium stages in total, and we have a reboiler and a partial condenser, we get in total 4.83. Now we need to recalculate that into physical trays, so we divide the number of equilibrium stages within the column with the overall tray efficiency, and we get 12.07, and we round that up to the nearest integer and get 13 trays. So 13 trays in total. The optimal feed location, if we want to calculate that into from equilibrium stages to physical trays, we do the same thing. So we divide the equilibrium stage with the overall tray efficiency and get 4.65, which means on tray 5, physical tray 5 inside the column. So remember, always answer with integer if you're asked how many physical trays or what the physical feed location will be. The B question concerned the minimum reflux ratio. So we start by identifying XD here. So the upper operating line should start in this point here at the diagonal where XD equals 0.7, and then we draw the Q line as before. And then we draw an upper operating line from here to the intersection between these two lines, the Q line and the system curve. And why do we do that? Well, we do that because if we try to step through here like this, we will never pass this point. As we come closer to this point, the triangles will be smaller and smaller and smaller and smaller, and we can draw infinitely many triangles, but we will never reach past that point. And we can calculate the reflux ratio by looking at the intersection here. It's 0.32, which means that the minimum reflux ratio is 1.19. Now, for some system curves, there is an inflection here, and that means that the minimum reflux ratio is not always given by the intersection between the upper operating line and the Q line, but rather like this, when it goes exactly through the system curve here as a tangent to the system curve. Because we can see here, if we try to draw triangles here, we will never pass this point here. So that's the minimum reflux ratio if we have a problem when we have a system curve that is severely depressed.